Week we're moving on to what I think might be the toughest chapter in the book, or one of the toughest. We're going to talk about solar and terrestrial radiation. So, with that, what does that mean? Basically, it's how energy flows into and out of the Earth and the atmosphere to maintain a stable and habitable planet. It's what it all encompasses. Without the energy coming into the Earth, we couldn't live the way we live. So, there must be something about this system, this energy coming in, that keeps us habitable and fairly stable. So what does that mean exactly? Well, let's start with talking about electromagnetic radiation. It's a form of energy, comes out of light bulbs, comes out of the microwave you use, and it can come from the sun and come from the earth. Both have electromagnetic radiation that comes out of them. So there are tons of wavelengths and we're going to talk about different aspects of electromagnetic spectrum as we go through the course here, especially this week. So let's a little bit understanding of what an electromagnetic wave is. If you've ever been out in the ocean and you get hit by a wave, a little bit later the water goes down, back down maybe to your knees, and then it gets hit again. Well, the peaks in those waves, the highest time is a wavelength between one peak to the next peak. And the same holds for an electromagnetic spectrum. So you get basically peaks between each aspect of the wave, and somewhere between the two you have a lower range. So, and the frequency is how fast those peaks pass you. The quicker those waves hit you, the more frequent the peaks are, the higher the frequency is. So, since all electromagnetic radiation moves approximately at the speed of light, or 186,000 miles per hour, the more peaks that are hitting you, the more energy that wave probably has. So, there's just the basic concept of a wave, an electromagnetic wave. You see them when you're looking outside at visible light. So, they're all over the place. What is a black body? A black body is at some temperature and absorbs all radiation it receives and emits all that it absorbs. A pure black body is a perfect absorber and emitter. So most objects are black bodies. Believe it or not, your body is a black body. It absorbs radiation and re-emits radiation. So there are certain laws that apply to a black body. For example, wavelength of the most intense radiation emitted by the black body is inversely proportional to its absolute temperature. So, for example, if that temperature is 100,000 degrees, 1 over 100,000 is going to be a really small wavelength. If that temperature is 70 degrees, 1 over 70, it's still fairly small maybe, but nothing like the one or the other. So if you were to look at that, the sun is a whole lot hotter than the earth, and both the earth and the sun are black bodies. That says that for 600,000 degrees, 6,000 degrees Kelvin, we have wavelengths right in this area here that would be the most likely towards ultraviolet. So that's where the most intensity is. And if you look at it, it's right in the middle of the visible spectrum. We see the visible light basically because that is generated by the sun's radiation. Most of the radiation from the sun is in that spectrum. The earth, on the other hand, the infrared radiation from the earth, the wavelength's a little bit longer. So it's over here somewhere. So it's not being seen by us. So that means that we have to have other instruments to record that radiation. Another factor is, guess what? A temperature to the fourth power is how much energy is emitted from a black body. So you think about the sun compared to the earth, there's going to be a huge difference here. So that's why the sun emits so much more radiation than the earth does. All right. here's an interesting thing. We consider the Earth to be basically one astronomical unit. Mars is much closer, so it's less than one. Mars is much further, so it's more than one. So what we can learn is that the energy that's being received by a planet is 1 over the radius squared from the sun. So if that radius, we'll say, I don't know which planet it might be, but say it's 6 times 6 units, that would be 1/36th the amount of energy it received compared to what the Earth has. So you can see that's really, really reduces the amount of energy being absorbed by any planet, depending on how far away you go from the sun. But it doesn't take a lot to get pretty low. So there's another aspect to the sun, and this is a great little experiment if you want to play with it. You can take a flashlight and point it straight down, and you'll see a small circle. If you angle that flashlight, that circle becomes much bigger. Think of that flashlight as being the sun. So if you're at the equator, where the sun is pointing directly at you most of the year, or right around the equator, you're getting that small circle. We live up between 30 and 40 degrees north, so take your angle at 30 to 40 degrees, we'll say, or even more than that sometimes in the wintertime, and notice how much more the light spreads out, that energy spreads out. That's why in winter, we don't get as concentrated or as much solar radiation as you do in the summer in our latitude. And if you're at the equator, think about it, you're not getting a whole lot sometimes. But we'll call about altitudes. And here on this picture, you can see, for example, at 40, if it was right at solar, when the sun is directly at the equator, which is coming up in March, then our angle of solar radiation would be probably 40 degrees, I think is about what most of our areas around latitude. But if you're at the North Pole, it's 90 degrees. So, man, that's really cutting it kind of shallow angle there. So you can see the difference here on the angles, how the sun is not coming in directly to where you are, spreading out that radiation over a larger and larger area the further north or south it gets. And with that, here's a measurement of the radiation. You can see Singapore is very close to the equator. Doesn't change a whole lot. However, Brockport, New York, which is similar latitude to where you are, for example, you can see in the wintertime it goes way down, and in the summertime it comes way up. So though you actually have more energy in the summertime than the equator receives. Now, if you're at Antarctica, look in the summertime, our summer, their winter, and you can see nothing. No solar radiation whatsoever is reaching there. And the reason that is, the Earth has a tilt. And that tilt never changes as it's moving around. But if you move an object around and we look at that tilt, here's winter solstice. For us, December 21st, you can see the sun is shining in the southern hemisphere more because our end is tilted away. Oh yeah, a curious fact is the sun's actually closer to us in the winter than it is in the summer. So it's a little further away from us in the summer. So you can see the tilt. Even though the Earth never changes its tilt, it changes its tilt relative to the sun. So the atmosphere. Within the atmosphere, a certain part of the atmosphere reflects radiation, some of it's absorbed, and some of it is kept on transmitted into the Earth. So all of that adds up to 100%. Well, scattering, what is that? Well, the reason we see blue sky is there's scattering from oxygen and nitrogen molecules. That scattering causes basically the blue violet light to be what you see. It's a preferential scattering of those molecules. But a cloud scatters it. That's why if you have a dark cloud over your head, it's cooler because the sun's radiation is hitting that top of that cloud and is scattering. So not all of it. It goes out in every direction when it does that. Reflection is just another means of scattering. Reflection is things like ice, snow, for example, where everything, almost all that radiation that came into the ground on a very white surface is being reflected back out. However, you think about it at summertime, a very black asphalt, for example, that absorbs almost all radiation. Black body, in essence, really can feel it. And that makes it that much hotter. So there's another thing in the atmosphere. Some of the energy due to greenhouse gases can be absorbed by the atmosphere. And part of that happens in the ozone layer up in the stratosphere, where some of the ultraviolet radiation is involved in the chemical reactions that occur in the ozone, and it significantly reduces the intensity of that ultraviolet radiation. Another thing you can really see on satellites, if you have snow cover, it's going to stay colder because the snow is reflecting a lot of that sunshine. So here is basically a table of about 30% of the radiation that reaches Earth is reflected back to the sun. Another 23% is absorbed by the atmosphere. Another 47% is absorbed by the Earth's surface. So the Earth is actually being heated up. So that's a general budget of how the solar radiation is impacting it. And you can really see that in evidence if you look at the temperatures at the Earth's surface. Next to the ground is where it's hottest. That's because the Earth is the source of heat for the lower part of the atmosphere. Now, the greenhouse effect is what makes our Earth habitable. Infrared radiation, a different wavelength than the sun's radiation, is absorbed by greenhouse gases. So, these are longer wavelengths than the actual ultraviolet radiation that comes in from the sun. And this is heats up and absorbs those gases, and it heats up the atmosphere by it. So, for example, the main contributor to greenhouse gas is water vapor. The more water vapor in the atmosphere, the less heat can be released back into out from the Earth. Carbon dioxide is the next biggest. Methane actually is pretty significant, 4 to 9% of a greenhouse gas, and methane is extremely low amount in the atmosphere, but it's very efficient at absorbing infrared radiation. And there are different windows of infrared radiation, and we're going to look at those. One of the interesting things is, think about the Gulf Coast versus the Southwest. The Gulf Coast has a lot of humidity, so it is going to absorb a lot of energy in the water vapor there. It's going to stay higher air temperatures at night because when the Earth is trying to emit that infrared radiation back out at night, it's absorbed by the water vapor and it keeps the atmosphere warmer. So that's why the temperatures are warmer in the southeast, or where it's a moist climate, compared to the desert southwest, where all that radiation is getting reflected back out into space at night, and it cools off very quickly. One final thing is, we talk about greenhouse gases and the Keeling curve, which is basically carbon dioxide, and we know that the Earth is warming. The question is, how is it related to CO2 or other gases? And a big question, obviously, is it man-made or not? And they're not easy answers. One thing we do know is the more CO2 that is in the atmosphere, the warmer the atmosphere gets. That's just a fact. So if you monitor the fact that carbon dioxide has been increasing, and the atmosphere is getting warmer. Oh, that's what the calendar effect is all about. So with that, the only thing I really wanted to show you extra today is we talked a lot about different curves, different infrared radiation that comes back out. Well, we have satellites, and I'm going to just deal with GOES satellites right now. And GOES satellites are designed to measure different wavelengths. So we've talked about geocolor, which is basically taking every wavelength that comes out and making a nice pretty picture of it. But say I wanted band 1, which is 0.47 microns. That's a blue shade of visible light. So what you're seeing there is going to have a tendency to look more towards the blue range of light. Or you can have the red range of light, 0.64. And then there's another band. Vegetation tends to emit a lot of infrared radiation at about 0.86. Cirrus, a higher cloud, 1.37. Snow and ice, a different band. You can get the picture real quick here that if you know a channel in the Earth of infrared radiation, you can get a whole lot of information about the atmosphere from those infrared radiation. What level that might be. We can look at upper level water vapor by looking at one set of channel of infrared radiation. We can get mid-level or low-level by looking at other ones. Then there's things called clean long wave, which is basically all that channel of infrared radiation is not absorbed by any greenhouse gas. So it just comes straight out. So you can look at that one. So you can see each one of these gives more information about the clouds and about the structure in the atmosphere. That's why the new GOES 16s that have 16 channels like this, GOES 17 is out there, these are phenomenally better for understanding the atmosphere with. So if you have any questions about this, and you might, let me know, and I'll be happy to help.